13x squared minus 15x to the 2/3, all that raised to the 5th power. So the derivative f prime of x is something to the 5th becomes 5 times that something to the 4th power. And the chain rule says take the derivative of that something, and that would be 84x cubed minus 16x minus 10 times x to the negative 1/3. Number 2, g of x is cosine squared of 2 to the 3x divided by 3x minus 2. G prime of x, this is a function within a function within a function. The innermost function is this quotient. The next function is the cosine, and the outer function is something squared. So the derivative is 2 times that something to the 1st power times 2 to the 3x over 3x minus 2 times the derivative of the cosine. The derivative of the cosine is minus the sine of still the same thing, 2 to the 3x over 3x minus 2. Now times the innermost, which is a quotient. The derivative of 2 to the 3x is 2 to the 3x, but its base is not e, so we have to do natural log of the base. And the exponent is not just x, it's 3x. We have to take the derivative of that, times 3. Times the denominator, 3x minus 2. Subtract the numerator, 2 to the 3x, times derivative of the denominator, 3. All of that divided by 3x minus 2, quantity squared. And there's a common factor 3 here, which we could combine with that 2 there to make a negative 6 times all that. So it could be simplified a little bit. Or, if we want to get creative, 2 cosine something sine something is sine of twice that something. So it would be minus the sine of twice that something. So there are several ways that if you want to go further in simplifying it, perhaps you could take it another step or 2 down. And also the common factor 2 to the 3x could come out. So, but again, what I was looking for, can you find the derivative? Not can you find the derivative and then make mistakes simplifying it. But if you made mistakes simplifying it, then I had to take something off. You know? Okay, number 3. This is a f of x is equal to the inverse tangent of e to the 2x, e to the 2x close, times the natural log of 2x plus 3 plus the inverse sine of 3x times logarithm base 6 of 5x plus 1. Okay. So f prime, this is a sum of 2 products. So we do the first product and then add the second product. So the derivative of the first product is, inverse tangent is 1 over 1 plus x, in this case e to the 2x. So that's e to the 4x, 1 plus x squared. Chain rule, times 2 e to the 2x times the second factor, natural log of 2x plus 3, plus the first factor, inverse tangent of e to the 2x, times derivative of natural log is 1 over 2x plus 3 times the chain rule, derivative of 2x plus 3 is 2. Took care of that. Plus, inverse sine is 1 over square root 1 minus 3x squared, 9x squared, chain rule times 3 times the second factor, logarithm base 6 of 5x plus 1, plus first factor, inverse sine of 3x, times derivative of the second factor. It's a logarithm, so we're going to get 1 over 5x plus 1. But because it's not base e, we have to divide by the natural logarithm of the base. And chain rule says 5 times. So that is number 3. Yes?
The 2 in front tangent, if it is not multiplying
Didn't put my 3 in front of the sign?
the 2 tangent in that one. If it, I leave it outside, not multiplying, is it affected?
This goes with that. Okay? Because we have a product here plus a product here. The derivative of the first product is that. Derivative of the second product is that. Number 5, as I said, we'll come back to 4. We're given f of x is equal to x cubed minus 9x. And we say that negative 4 is less than or equal to x, it's less than or equal to 5. So we want to examine the endpoints anywhere the slope is 0, or if we have any cusps or vertical asymptotes, we look for things. So the derivative f prime of x is 3x squared minus 9. We set that equal to 0. Divide by 3. Solve for x. Okay. So this gives us 4 points to look at. The x values being negative 4, negative square root 3, positive square root 3, and positive 5. The endpoints plus the places where the slope is 0. Plugging those into the original, negative 64 plus 36 gives negative 28. Plugging in negative root 3, we get negative 3 root 3 minus 9 root 3 is negative 6 root 3. I'm sorry, it's plus 6 root 3. Negative 3 root 3 plus 9 root 3 gives a positive 6 root 3. Plugging in positive root 3, we end up with a negative 6 root 3. And plugging in 5, 125 minus 45 is 80. So those are the 4 points. Now all we have to do is decide what those 4 points represent. And let's see. Get down there in a minute. Fiber. On my Fran. Wait. Okay. So, if we examine the slope at -4, positive 48 minus 9, positive, what was that, 39. So from this point, it goes uphill. So this must be a minimum. And observing the last point, plug 5 in here. 5 squared is 75. 25 times 3 is 75, minus 9 is 66. So again, it's positive, and we're going positive to get up to here. So this is a maximum point. And the slope here and here is 0. But slope to the left of this is positive, slope to the right of that is negative. So this means this is a maximum. And in a similar argument, the slope of this one coming in is negative, and the slope going out is positive. So this is a minimum. And we look at the minima and see that this is the lesser of the two, so it is the absolute. Which means this must be relative. And in a similar fashion, we look at the maxima, and 80 is much larger than that, so this is the absolute. And this is the relative. Number 6. When I'm in a room with this much board space, it reminds me of this happened at one of those prestigious universities. A psychology professor had another colleague cover class one day because he had some business meeting or something. So he instructed the students, in the absence of their regular professor, that any time he was writing to the left and high on the board, look bored. And as he moved to the right and moved down, look more attentive. In just a couple of weeks, the professor is writing all his notes in the lower right-hand corner. People and dogs are easy to train. Just saying. Okay, number 6. G of x is the tangent of x. I picked this because we graph it from trig, 0, pi, 2 pi, pi over 2, 3 pi over 2. Asymptotic there, asymptotic there. Starts this, goes up, starts out here, comes up, goes up, and then finishes here at 2 pi, pi. But we're interested in pi over 4. And 4 pi over 3. So we're not interested in that at all. We're just interested in there to there. By inspection, this is the lowest point in the neighborhood. Only way you can go from there is up. From here, the only way you can go is down. So this must be a minimum, and that's a maximum. And here we have vertical asymptote. So let's go and take derivatives. G prime of x is secant squared of x, which, by the way, we note is never 0. The minimum value of secant squared is positive 1, and it goes up from there. So we have no place where the slope is 0. So there are 3 values I want to look at. Pi over 4, pi over 2, and 4 pi over 3. At pi over 4, the value of the tangent is 1. At pi over 2, it is undefined. And 4 pi over 3, it is square root 3. Again, when you're leaving here, you're going uphill to the right. So this means this is a minimum. And clearly it's not the lowest of the low. The lowest of the low is approaching negative infinity. So this is a relative minimum. And similarly, at the point 4/3 pi gives root 3, this is a relative maximum. So the only thing required was to find these. Didn't have to do that. But since it's there, why not? Okay. Number 7. Find the values of C such that f prime at C is equal to the slope of the secant line for the interval. F at B minus f at A over B minus A, where B and A are basically -3 to +4. So let's find this value. Oh, I have to have a function. The function is x plus 2 times x minus 1 times x minus 3. Okay, by direct substitution, my f prime at C that I'm interested in is f at -3. Well, let's see, that's -1 times -4 is +4 times -6 is -24, but we're going to subtract that. Plugging in +4, and it's 6 times 3 is 18 times 1 is 18. Denominator, we have 4, subtract -3. Do that arithmetic, we get 6. So, let's find the derivative of f prime. The derivative of f prime is, we have a product of 3 terms, 3 factors I should say. Derivative of the first, 1, times the second, 2, plus the first times the derivative of the second, 1, times the third, plus the first times the second, times derivative of the third, which is 1. So this is our derivative. And it's pretty easy since these is just binomials. X squared minus 4x plus 3 plus x squared minus x minus 6 plus x squared plus x minus 1. Add those together, we get 3x squared. Let's see, minus 4x minus 5x plus x is minus 4x plus 3, minus 6 is negative 3, minus 1 is, I did that wrong. This is 2. No, I did something wrong. 3 minus 6 is negative 3, minus 2 is negative 5. So this is f prime. Well, we want to find the values of c that make f prime equal to 6. So we have this equation to solve. 6 is equal to 3x squared minus 4x minus 5. That is, 0 is equal to 3x squared minus 4x minus 11. That does not factor, so we use the quadratic formula. X is equal to minus b plus or minus square root b squared minus 4 times a times c plus 132, all divided by 2a. Let's see, this is 148, and 4 goes to 148, so for the short run, 4 plus or minus 2 times square root 37 over 6, which easily reduces to 2 plus or minus square root of 37 over 3. So these are the two values that give you that. Okay, back to number 4. Let's see, f of t is the square root of 3 sine 2x, or 2t, 3 sine 2t over e to the 2t plus 1. Okay, well, let's see. F prime of t is something to the 1/2 becomes 1/2 of that something to the negative 1/2, which can be expressed this way, e to the 2t plus 1 over 3 sine 2t. Times derivative of what's inside. And it's a quotient. Derivative of the numerator, 6 cosine 2t, times denominator, e to the 2t plus 1. Subtract the numerator, 3 sine 2t, times derivative of the denominator, which is 2 times 3, 6, e to the 2t plus 1, over e to the 2t plus 1 squared. Well, a bunch of this simplifies. Namely, this factor divides with those, leaving e to the 2t plus 1. This factor of 6 times 1/2 is 3. So I think I'll rewrite things as 3 times the square root of e to the 2t plus 1 over 3 times the sine of 2t times cosine 2t minus sine 2t over e to the 2t plus 1. So this is f prime. So F double prime is the derivative of the derivative. So let's see if we do that. F double prime of t. 3 times 1/2 times that thing, the negative 1/2, which turns it back over, 3 sine 2t over e to the 2t plus 1. Chain rule times the quotient, which is 2e to the 2t plus 1 times 3, 6, sine 2t minus the numerator, e to the 2t, times derivative of the denominator, 6 again, because it's 3 and 2. Derivative of sine is cosine. Cosine 2t divided by 9 sine squared 2t. Times the second factor, cosine 2t minus sine 2t divided by e to the 2t plus 1 to the fourth plus the first factor, 3 times square root of e to the 2t plus 1 over 3 sine 2t times derivative of the second, which is a quotient, derivative of the numerator minus twice the sine of 2t minus twice the cosine of 2t, derivative of the numerator times denominator e to the 2t plus 1 minus the numerator cosine 2t minus sine 2t times derivative of the denominator twice e to the 2t plus 1 divided by the square of the denominator, e to the 2t plus 1 squared. And again, we can simplify some. These, divide the square out there. We have minus 2 cosine 2t minus 2 cosine 2t is minus 4 cosine 2t, and minus sine 2t, and oh, I'm sorry, this, yeah, plus sine 2t adds out. So it could be simplified from there, but I'll quit at that point because we hit all the required steps of finding the derivative. So, simply because there are so many steps to get from, it didn't look that bad when I wrote it down, but you see that it is rather lengthy by the time you get to the end of it. So having said that, given everybody number 4 for free, which means the high score was 70 out of 70. The low score was about 40 out of 70. Having said that, this is the 12th week, is it not? And the nobody in here really falls into that category. That's in attendance today anyway. disaster waiting for you if you continue. But some people aren't getting the A+++ that they're expecting, so they bail. But then it's your choice. So if you plan to drop the course, you have to do it no later than this Friday or maybe Saturday, since there are some Saturday classes on the block. Not as many as there used to be. I have taught Saturday classes a couple of times. I hated that. It ruined my whole weekend. Okay? And I always end up with a 10:45 to 1:15. I mean, it starts early enough, you can't do much before class starts, and it ends late enough in the afternoon, it wastes your entire day. Sometimes I did a Friday, Sunday class. That wasn't as bad, because I still had all day Saturday to play. Sunday, and I'd have to get up and go to church anyway, so after church I'd go teach a class. No big deal. But I prefer not doing weekend classes. I think you probably are the same way. However, having said that, if that's the only way you can achieve your goal, you take a weekend class. Okay. If you feel like that I made a grievous error in scoring your exam, please share it with me before you get away today, so that we can make an adjustment if necessary. And the adjustment, no matter what you show me, will not be lower than what I already have marked on the paper. Okay, let's talk physics very briefly. We have displacement or position. We have velocity. We have acceleration. And the term beyond that, J, for jerk. And let's see. V is derivative of position. A is derivative of velocity. Second derivative of position. J is derivative of acceleration. Second derivative of velocity. Third derivative of position. Well, if our equation is complicated enough, it would be nice to use more than just the first derivative to help us in finding max and mins and sketching and whatnot. So, let's graph about 4 different graphs. Y equals x, y1. y2 equals x squared, y3 equals x cubed, and surprise, surprise, y4 equals x to the 4th. And let's find the first derivative of each. y1 prime is 1, y2 prime is 2x, y3 prime is 3x squared, and y4 prime is 4x cubed. And make a quick sketch of each of these from college algebra or below. You know the first is a diagonal line going through 1, 1, negative 1, negative 1. And has constant slope. So it says the derivative of that is 0. I'm sorry, the derivative of that is 1. Constant slope. This one, if we graph it, most of you recognize it as a parabola containing the points 1, 1 and negative 1, 1 and 0, 0 and curving upward. And it's the path of a free-hanging cable, not free-hanging cable, but a cable supporting a suspension bridge where the mass is directly proportional to the length of the bridge, not directly proportional to the cable. If it's directly proportional to the cable, then it's a catenary. We'll talk about those later on in calculus. But anyway, there's your parabola. This third one contains 0, 0, 1, 1, negative 1, 1, and curves sharply upward and downward. There we go. 1, 1, negative 1, negative 1, x 1. And this last one looks something like that. Contains the same 3 points that we started with. 1, 1, negative 1, 1, 0, 0. But as it comes through 0, it appears a little flatter and then climbs more sharply. So steeper climb and flatter through the bottom. Now, if we're driving a car on these roads, here it'd just be a straight drive, something like the Oklahoma Panhandle. Anybody drive out there lately? Long, straight, flat, boring roads.
Texas Panhandle's pretty bad too.
Yeah, or southwest Kansas. I mean, they're all kind of, and southeast Colorado. I mean, just, yeah.
Sucks.
This, left turn, left turn, left turn, left turn, left turn, all day long.
NASCAR.
Yeah. Except it doesn't close on itself like the NASCAR saying. This is more like Grand Prix. We go through the S's. Right turn, right turn, right turn. Wheel straight, left turn, left turn, left turn. This is kind of interesting. It looks like left turn, left turn, left turn, left turn, left turn. But as it passes through 0, 0, your wheels are momentarily straight. Let's look at second derivatives. Second derivative here is nada. Second derivative here is a constant 2. Second derivative here is 6x. And second derivative here is, what, 12x squared? Okay. Well, notice something. If the second derivative is positive, we're in the process of a left turn. If the second derivative is positive, we're in the process of a left turn. If the second derivative is negative, and this is negative to the left of 0, we're in a right turn. Well, that's interesting. Where you are in a left turn, they call that concave up. And where you're in a right turn, they call that concave down. So, the line has no concavity. Of course, driving down a flat road in Oklahoma, you may still have a chuck hole or two. It may cause a concavity to your rim and blow the tire. this is always in a curving upward. Whether it's pointed downward or not, you're still turning to eventually look like you're going up. This one, however, is right turn, right turn, right turn. If that curve would continue, it'd bring you back down. So, we have an interesting thing. It's called the second derivative test. If on where the function is continuous and its derivatives are continuous, if f prime equals 0 and let's say f prime at a is equal to 0 and f double prime at a is greater than 0, or f double prime at a is less than 0, or f double prime at a equals 0. There are some conclusions we can make. If the first derivative is 0 at some point, and the second derivative is positive, as is with a parabola, then this implies that we have a minimum. If the first derivative is 0, but the second derivative is positive, second derivative is negative, means it's concave down, that implies we have a maximum. If both the first and second derivatives are 0, the test fails. It doesn't tell us if we have a max or a min or something else. We have two examples of where the second derivative is equal to 0 and the first derivative is equal to 0. In this case, it's neither a max nor a min. In this case, it is a min. Oh. Where we're driving our vehicle, when we go from a right turn into a left turn, that point where the wheels are straight has a special name. It's called an inflection point. Here, even though the second derivative is equal to 0, it's not called an inflection point because you don't really change the direction of your curvature. And even though the curvature is infinity here, meaning it's flat, straight line, this goes from left to left. So, if I graph a nicer cubic, and I think the text has one that comes out reasonably nice. I want to say number 11 in section 4.4. Let's see if I guessed right. Chapter 4, 2, 4, 4, 4, 4, number. Let's see. Yeah, number 11 on page 251. Y equals x cubed minus 3x plus 3. Y equals x cubed minus 3x plus 3. And let's sketch the graph of this. I want to look at both the first and second derivatives. First derivative is 3x squared minus 3. If I set this equal to 0, it leads me to the two x values. X is either 1 or negative 1. If I look at the second derivative, it is simply 6x. So, let's plug these back into the original equation. See where those points are. We have negative 1 cubed is negative 1 plus 3 plus 3, positive 5. Plugging in positive 1, we have 1 minus 3 plus 3 is 1. At these points, first derivative is 0. Let's see what the second derivative is at that point. For the top point, 6 times negative 1 is negative 6. This was y prime. Let's do this one for the time being. Y prime at negative 1 was positive 5, and y prime at 1 was positive 1. Looking at second derivatives, y double prime at negative 1 is negative 6, which we note is less than 0. Y double prime at positive 1 is positive 6, which we note is greater than 0. So, this is wrong. 0, 0. This is the point, negative 1, 5. This is point 1, 1. Okay. So at point negative 1, 5, the first derivative is 0, the second derivative is less than 0, implies this is a maximum from the second derivative test. The point 1, 1, first derivative is 0, the second derivative is greater than 0, which implies this is a minimum. So if we sketch those that we have, 1, 2, 3, 4, 5, 1. Negative 1, 5, positive 1, 1. When x is 0, we get positive 3. We know it's a maximum here. We know it's a minimum here. So this thing has to do something like that. It didn't give us that value, but our calculator will. If we put x cubed minus, we put SOLVE, paren, x cubed minus 3 times x plus 3 equals 0, comma, x close, it will give us that point. So, we have a reasonable sketch of the curve. We didn't have to decide what's the slope to the left of this, what's the slope to the right of that, what's the slope to the left of this, what's the slope to the right of that. We just look at the second derivative. Second derivative says concave down, so it's got to be a maximum. Second derivative says concave up, so it has to be a minimum. Okay, let's look at number 17. x to the fourth minus 2x squared. Y equals x to the fourth minus 2x squared. They go on and point out that that factors. And I think the reason they point out that this factors is so we can find the zeros of the function rather easily. We have x squared times x squared minus 2. So the zeros of this function are negative square root 2, 0, and plus square root 2. Let's go and find the derivative. Y prime is 4x cubed minus 4x. Set this equal to 0, solve it. We have 4x times x squared minus 1. Well, that gives us that the slope equals 0 at these points. Let's see. Negative 1, 0, positive 1. And at negative 1, the original function is 4 minus 2, negative 1. 0, it is 0. And at positive 1, it is negative 1. And let's look at the second derivative. Y double prime is equal to 12x minus 4. I'm sorry, 12x squared minus 4. So let's look at, since first derivative is 0 for these 3 points, let's look at the second derivative. Y double prime at negative 1 is 8. Which is greater than 0. Y double prime at 1 is also 8. Which is greater than 0. Y double prime at 0 Y double prime at 0 is negative 4, which is less than 0. So let's identify these 3 points. First derivative 0, second derivative is greater than 0, means a min. First derivative 0, second derivative negative, means a max. First derivative 0, second derivative greater than 0, means a min. Okay. Let's plot all these things. And okay. 1, 2, 1, 2, 1, 2. I think we fit most things in there. The zeros of the function are negative square root 2, 0, 0, 0, and positive square root 2, 0. Square root 2 is about 1.414. Okay. Now let's plot our max and mins. Negative 1, negative 1, 0, 0, positive 1, negative 1. And we know this is a min, this is a min, this is a max. So we connect all these with a smooth curve, and we get a nice W shape. Now we can go on and let's find a couple of points. If we set Y double prime equals 0, and solve, we get 3x squared minus 1, which means x is plus or minus 1 over the square root of 3. And that's about 0.577. So when x is about 1 over the square root of 3, I'm put in here, we get 9 minus 6. Did I do that right? No. 9. No, 1/9. Correction. 1/9 minus 2/3. 1/9 minus 6/9 is -5/9. So at about 0.577, we're at about -0.59. And same thing over here at -0.577, we're at -5/9. And those are where the inflection points are. Because here, right turn, right turn, right turn, right turn, right turn, left turn, left turn, left turn, right turn, right turn, right. Said that backwards, didn't I? This is a left turn. Left turn, left turn, left turn. To that point, wheel straight. Right turn, right turn, right turn. Wheel straight. Left turn, left turn, left turn. So we have our inflection points as well. So we can get all that information before we draw the graph. Okay. But having said that, don't forget one peak at TI-89 helps a lot if you're having trouble visualizing what something is doing. But based upon this information, we know that we don't need a huge window this way or a huge window that way to get everything to fit in. Sometimes if you make your window too large, the detail down close is harder to figure out. But again, this isn't correct until we get some labels and scales . There we have a reasonably sketched graph. Okay. On that same set, I think I'm looking at number 31. Y equals x over x squared plus 1, square root of x squared plus 1. Equals x over square root x squared plus 1. Y prime, quotient, derivative numerator 1 times denominator square root of x squared plus 1 plus the numerator x times derivative denominator 2 times square root x squared plus 1 times 2x. Those 2's divide out. Minus. Divided by square root of x squared plus 1 squared. I think if I multiply through by a well-chosen 1, it simplifies a little. This becomes x squared plus 1. This divides out, minus x squared. The denominator becomes x squared plus 1 to the 3 halves. Since that divides out, this is 1 over, friend, x squared plus 1 to the 3 halves. That's my y prime. Notice, the only time a fraction can be 0 is if its numerator can be 0. Can the numerator ever be 0? No. Do we have any vertical asymptotes? That is, can the denominator be 0? No. This thing is always positive. It's always going up. It's symmetric with respect to the origin, as it behaves like an odd function. So, since we don't have any place where the slope is 0, let's just plot some points. When x is 0, y is 0. When x is positive 1, we have 1 over square root of 2. And 1 over square root of 2 is about 0.7. When x is negative 1, we have negative 1 over square root of 2, which is about negative 0.7. At 0, the slope is 1. 0 plus 1 is 1, 2 3 halves is 1, 1 divided by 1 is 1, so the slope is 1. So it looks like it's going in there, so slope is 0. So if we kind of, in intuitive, that kind of goes like this kind of goes like that. Oh, that kind of looks like an inverse tangent, doesn't it? But it's not, because this does increase without bound. No, I'm sorry, it doesn't. It has a horizontal asymptote equal to 1. But it doesn't matter how far out to the right you are. The second derivative is the derivative of this. Let's see, y prime is equal to x squared plus 1 to the negative 3 halves. Means y double prime is equal to negative 3 halves times x squared plus 1 to the negative 5 halves times 2x, which is 2's divided negative 3x in the numerator and x squared plus 1 to the 5 halves in the denominator. And when x is positive, this has a negative second derivative, which means concave down. This portion is turning to the right, it's concave down. And when x is negative, numerator here is positive, so it says concave up. This is concave up. So, again, one peak is worth a lot of estimating.
You put into the TI and then just put in the original function.
Yeah, say graph the original function. And, you know, at the beginning you may not know what limits you ought to be looked at. So if you put it on a standard screen is what, 10, 10, 10, 10, 10. So, but it would be kind of hard to tell because it looked about like that. You'd have to pick a better window once you have more of a concept of what it's doing. So just because it's concave down does not mean it has the maximum point. Positive 1 is the limit, but the function never achieves that value. Negative 1 is the limit, but function never achieves that value. Okay. Whew. Oh, by the way, if I have x1 and the root x1 plus 1, what's the tangent of this angle? The tangent of that angle is looking for the tangent of some angle has that value, then basically we're doing an inverse tangent type drawing. Okay, let's shift gears a little bit and look at section 4.5. And who knows French in here? Anybody speak a little bit of French? Anybody read a little bit of French? When I was in 5th grade, we did about 3 days worth of French. And we got down to Como Talibou, Très bien, merci, et vous. Yeah, that's it. I'm done.
I had to take French whenever I was going to school overseas. It was required. Not do I remember anything of it? Of course not.
Well, here's your chance to shine. Please if I put an S in here, hospital means the hospital. A hospital is a pseudonym for some guy. I think it's in the book somewhere. He's not the most important of all mathematicians, so I don't remember what it was. But L'Hopital. We have L'Hopital's rule. And the problem is, if we have limit as x approaches some value a of f of x over g of x has the form 0 over 0, that is, f of a equals 0, g of a equals 0, then we don't know what that limit is. But L'Hopital comes to the rescue. And there's a proof for it in the text. Again, at this level, I don't care about the proof. If I were teaching advanced calculus, the proof would be important. But suffice it to say that, if this limit appears to go to 0 over 0, then this limit as x approaches a of f of x over g of x is the same as the limit as x approaches a of f prime at a, f prime of x over g prime of x. That's the first case. The second case is if limit as x increases without bound in the positive or negative direction of f of x over g of x takes the form of infinity over infinity, then this still applies. That means then limit as x approaches infinity of f of x over g of x is equal to the limit as x approaches infinity of f prime of x over g prime of x. And we'll look at a logarithm case a little later, but let's look at this right now. Let's look at a reasonable function. Let's look at the limit as x approaches 0 of 3 times x minus the sine of x over x. Okay. By direct substitution, we have 0 over 0, because 3 times 0 is 0, sine of 0 is 0, x is 0, we have the form 0 over 0. Now, this one, we could algebraically simplify. Well, let's do it by algebraic simplification, and then let's also do it by L'Hopital. Algebraic simplification says the limit of the sum is the sum of the limits. Let's rewrite this as limit as x approaches 0 of 3x over x plus the limit as x approaches 0 of minus the sine of x over x. And this one, clearly the x's divide goes to 3. And this one, sine x over x, we proved was equal to 1 because we needed that to find the derivatives of sine and cosine. Minus 1. But if I did not know that it could be broken up nicely algebraically, I could still apply L'Hopital. That is limit as x approaches 0 of 3x minus sine x over x is equal to the limit as x approaches 0 of the derivative of the numerator, 3 minus cosine of x, over the derivative of the denominator, 1. Now by direct substitution, cosine of 0 is 1, 3 subtract 1 is 2, 2 divided by 1 is 2. So, that's kind of nice. It will save us some painful work in some cases. Let's look at on page 262. Let's start with one that also we probably know algebraically. Number 9. What do we have? T cubed minus 4t plus 15. T cubed minus 4t plus 15 divided by t squared minus t minus 12. T squared minus t minus 12. And they want to look at the limit as x approaches, what's that, negative 5?
Negative 3.
Okay, thank you. Limit as x approaches negative 3. Plugging in negative 27 plus 12 plus 15 is 0. Positive 9 plus 3 is 12, minus 12 is 0. This has the form 0 over 0. Bummer. So, let's take the derivative of numerator and denominator. We will get the same limit. Limit as x approaches negative 3 of 3t squared minus 4 over t minus 1. Now by direct substitution, we don't have an issue. 27 minus 4, 23. Negative 3, subtract 1, negative 4. Which one did I see that looked nice? Let's look at number 14. sine of 5t over 2t, the limit as x approaches 0. Approaches 0 of the sine of 5t over 2t. Yes?
On that last one,
Did I make a mistake?
yeah, shouldn't it be 2t minus 1?
Oh, man. Yes. 2t minus 1, in which case, that's negative 6 minus 1 is negative 7. This is still positive 27 minus 4. Yeah. Thank you for correcting me. Once again, I demonstrate I can do arithmetic incredibly quickly, and sometimes I get the right answer. This one, it could be done algebraically simplifying it, because 5t is equal to t plus 4t. Use the sum of two angles. And then I'd have some terms with t and 4t. So then I break down the 4t into t plus 3t. Then I have the sum of t's and 3t's. Further, could break that down into t plus 2t. And finally break the 2t down into simply t's. Sines and cosines, sines and cosines. So I end up with a numerator that big over 2t. Or imply L'Hopital. Because plugging in 0, the sine of 0 is 0. Twice 0 is 0. So let's apply L'Hopital. It says, what is the limit as t approaches 0 of 5 times the cosine of 5t over 2. And here, plugging in 0, 5 times 0 is 0, cosine of 0 is 1, 1 times 5 is 5, 5 halves. It's like that when it comes out. So simply. So, there were several that were the form 0 over 0. Let's look at a couple that have the form infinity over infinity. See if we can find some. Number. Number 32. Log base 2 of x over log base 3 of x plus 3. Limit as x increases without bound. Log base 2 of what? Over log base 3 of what? Limit as x increases without bound. Number 32. Log base base 2 of x over log base 3 of x plus 3. Okay. So, if the base of the logarithm is greater than 1, logarithm increases without bound. So by direct substitution, log base 2 of infinity is infinity, and log base 3 of infinity plus 3 is infinity. Now this is the form infinity over infinity, but again, we can apply L'Hopital. And we have, this is the limit as x increases without bound. The derivative of the first one is 1 over x divided by natural log of 2. The derivative of the denominator is 1 over x plus 3 as natural log of 3. Which if we invert and multiply, we get limit as x increases without bound of x plus 3 natural log of 3 over x natural log of 2. Now, this still gives us infinity over infinity. Natural log 3 is a constant, natural log 2 is a constant, but we still have x infinity plus 3 over infinity, still infinity over infinity. Well, if applying L'Hopital once doesn't get it, you apply L'Hopital a second time. Limit as x increases without bound. Derivative of this is 1 times natural log 3. Derivative of this is 1 times natural log 2. Natural log 3 over natural log 2. Or if you want to write it as a base, that's the same as log base 2 of 3. Just saying. But this is the acceptable answer. Okay. As I said, there's also a logarithm issue. If we have the form 1 to the infinity, or we have the form well, no, let's go the other way. Well, let's look at one. Let's look at problem number number 53. The limit of the natural log of x to the 1 over x as x increases without bound. Limit of natural log of x to 1 over x as x increases without bound. So this is of the form infinity to the 0. Doesn't behave very nice. So, but if I have this indeterminate form, let's do this. If the limit of some f of x as x increases to infinity has the form, or let's just say this is L. Then the limit as x approaches infinity of the natural logarithm of f of x is natural logarithm of L. So let's start here and work that way. In other words, if I take the limit of its logarithm and get a nice number, then all I have to do is exponentiate to get back to the original L. So I want to examine the limit as x increases without bound of the natural logarithm of x, the 1 over x. See, that looks worse. Well, it's not really, because this comes out as a coefficient. The limit as x increases without bound of the 1 over x comes out as a coefficient. Now if we look at this, sure enough, as x increases without bound, log of x goes to infinity, log of infinity is infinity over infinity. Now we're in a more useful form, infinity over infinity. We apply L'Hopital's rule. The derivative of the numerator. Derivative of the natural logarithm is 1 over what we had times the derivative of what we had. That's derivative of the numerator. Derivative of the denominator is 1. Now here, as this goes to infinity, we have 1 over infinity times infinity. 1 over infinity is 0. So, the limit of the logarithm of the limit is 0. To get back to our limit, we exponentiate. An interesting limit that you come across in this has form 1 to the infinite power. Also breaks down nicely using logarithms. So save time and energy. This is E. That's one way to define the value of E, is the limit of 1 plus 1 over n to the n. This is also how they develop the formula for continuous interest. You know, if you have compound interest, the amount of money you have is equal to the initial amount times 1 plus the annual rate divided by the number of compoundings per year to the nt compound. Continuous e to the RT, where R is the annual rate of interest. Given the same interest rate, the best return on your money is continuous interest. I was growing up during the time they were transitioning from semi-annual or quarterly interest, because they didn't have high-speed computers, So they're doing this all based upon tables of values, because slide rule wasn't accurate enough, and raising things to larger powers is a mess, so they would use tables. And when they first started coming out with computers that could crunch larger numbers, they said, well, the bank across the street is compounding quarterly, so we'll do better, we'll compound monthly at the same rate, which means a little higher overall. Well, then the bank across the street says, well, if they're doing it quarterly, monthly, we'll do it weekly. And then the other guy says, well, they can do it weekly, we can do it daily. And finally, someone says, well, if they can do it daily, we'll do it continuously. And that's the best rate you can get for a given APR. Which comes from this kind of stuff. All right, let's do another of those. Let's look at number 61. Limit as x increases without bound of x plus 2 over x minus 1 to the x. X plus 2 over x minus 1 to the x. Limit as x increases without bound, x plus 2 over x minus 1 to the x. By direct substitution, basically we have 1 to the infinity. And that form is the opposite of infinity to the 0, but it still works if we apply natural logarithms. So, we want to look at the natural logarithm of this, which gives us limit as x increases without bound of x times the natural log of x plus 2 over x minus 1. And again, as x increases without bound, well, this isn't bad. As x increases without bound, this limit is 1 in here. Log of 1 is 0. We have 0 times infinity. 0 times infinity is one of the forms we can look at, because I think I'll rewrite this as the limit as x increases without bound of the natural log of x plus 2 over x minus 1 over 1 over x. Now as x increases without bound, we have 0 over 0. I can take the derivative of both of these. The derivative of the numerator, limit as x increases without bound, is 1 over what we had. So it'll be x minus 1 over x plus 2 times the derivative of what we had. It's a chain rule thing. Derivative of numerator times denominator minus numerator times derivative denominator over denominator squared. Derivative denominator, x to the minus 1 becomes minus 1 over x to the minus 2, or 1 over x squared. Let's simplify this if we can. X minus x goes away. Negative 1 minus 2 is negative 1. So I'm looking at limit as x approaches infinity of x minus 1 over x plus 2 times, what did I say this was? Negative 3 over x minus 1 squared over x squared. Let's change the minus sign. Okay. One of these divides with one of those. Let's bring this back upstairs. We have the form x squared over x plus 2 times x minus 1. On the limit as x increases without bound. Multiplying this out, we have x squared over x squared plus x minus 2. Limit as x increases without bound. I know this because this is a polynomial over a polynomial. If the degrees are the same, the limit is the ratio of the leading coefficients. But if you didn't recognize that, we do this twice more. 2x over 2x plus 1, 2 over 2, finally gets us down to 1. Remember, this is the natural logarithm. This is the natural logarithm of the function we're looking for. So, this limit is 1 elevated to e, or e elevated to this is terrible.